Unlocking universal quantum computing, the power of Neglectons explained. Imagine a world where the discarded becomes the cornerstone of revolutionary technology. What if the key to unlocking universal quantum computing wasn't some shiny new discovery, but something that had been overlooked all along? This is precisely what a team of researchers has proposed, breathing new life into particles once dismissed as irrelevant. These rescued particles, now playfully called Neglectons, could be the missing piece in the quest for robust and scalable quantum computers. Quantum computing holds immense promise, with the potential to solve problems that are currently far beyond the capabilities of even the most advanced supercomputers. However, one major obstacle stands in the way: fragility. The basic units of quantum information, known as qubits, are incredibly sensitive to disturbances from their environment. This sensitivity leads to errors that can quickly snowball, rendering computations unreliable. To address this challenge, scientists have been exploring an innovative approach called topological quantum computing. This method seeks to protect quantum information by encoding it in the geometric properties of exotic particles known as anyons. These particles, theorized to exist in certain two-dimensional materials, are believed to be far less vulnerable to noise and interference compared to traditional qubits. Among the most promising candidates for this approach are Ising anyons, which are already being extensively studied in condensed matter physics labs due to their potential presence in systems like fractional quantum Hall states and topological superconductors. But here's where it gets tricky. While Ising anyons offer a significant advantage, they aren't quite enough on their own. Their computational power relies on a process called braiding, where anyons are physically moved around each other to perform quantum logic operations. Unfortunately, braiding Ising anyons only supports a limited set of operations known as Clifford gates, which don't provide the full functionality required for universal quantum computing. Enter the breakthrough. In a recent study published in Nature Communications, a team led by researchers at USC has unveiled a surprising solution. By introducing just one additional type of anyon, a particle previously disregarded in conventional models, they've demonstrated that Ising anyons can achieve universality. In other words, they can perform any quantum computation through braiding alone. This newly recognized particle has been given the nickname Neglecton, a nod to its prior status as an overlooked entity and its newfound critical role. The Neglecton emerges naturally from an expanded mathematical framework and fills the gap needed to complete the computational toolkit. So, what makes Neglectons so special? The answer lies in a novel class of mathematical theories known as non-semisimple topological quantum field theories, TQFTs. These theories extend the standard semi-simple frameworks that physicists typically rely on to describe anyons. Traditional models discard objects deemed useless because they possess what's called quantum trace zero. But as Aaron Lauda, professor of mathematics, physics, and astronomy at USC Dornsife College, explains, those discarded objects turn out to be the missing piece. It's like finding treasure in what everyone else thought was mathematical garbage. The beauty of this new framework is that it retains these neglected components, revealing the existence of the neglecton. When combined with Ising anyons, this stationary neglecton enables universal quantum computation via braiding. Remarkably, only one neglecton is required, and it remains fixed while the Ising anyons are braided around it. Of course, integrating this concept wasn't without its hurdles. One major issue arose from the fact that the non-semisimple framework introduces irregularities that violate unitarity, a fundamental principle ensuring that quantum mechanics preserves probability. For many physicists, this would have been a deal-breaker. However, Lauda's team devised a clever workaround. They designed their quantum encoding to isolate these irregularities away from the actual computation. As Lauda puts it, think of it like designing a quantum computer in a house with some unstable rooms. Instead of fixing every room, you ensure all of your computing happens in the structurally sound areas while keeping the problematic spaces off limits. By carefully controlling where quantum information resides within the theory, They ensured it stays in the parts that behave properly, allowing computations to proceed despite the unconventional global structure. This breakthrough underscores how abstract mathematics can unexpectedly solve real-world engineering challenges. By embracing mathematical structures once considered useless, we've opened a whole new chapter for quantum information science, Lauda remarked. The implications of this work are profound, both theoretically and practically. On the theoretical side, the team is working to expand their framework to other parameter values and to better understand the role of unitarity in non-semisimple TQFTs. Experimentally, they aim to identify specific material platforms where the stationary neglecton might arise, and to develop protocols for translating their braiding-based approach into practical quantum operations. What's particularly exciting is that this research brings us closer to achieving universal quantum computing using particles we already know how to create. The math gives a clear target, Lauda explained. If experimentalists can find a way to realize this extra stationary anion, it could unlock the full power of Ising-based systems. And this is the part most people miss. The journey from pure math to quantum reality isn't always straightforward. Sometimes the answers lie in the unlikeliest places, like the discarded pieces of a puzzle. So, here's a thought-provoking question for you. Are there other hidden treasures in the world of science waiting to be rediscovered? Share your thoughts in the comments below. Unlocking quantum computing. The power of neglectons. Quantum computing's hidden hero could be a neglecton. Imagine if the solution to a major hurdle in quantum computing lay hidden in what everyone else had thrown away. But here's where it gets controversial. By reviving a single discarded particle, researchers claim they've paved a direct path to universal, fault-tolerant quantum machines. Topological quantum computing has long thrived on the promise of noise-resistant quasi-particles called Ising anyons. These exotic entities encode information in knots and braids, letting us compute simply by weaving them around one another. Yet, despite their elegance, braiding Ising anyons alone can only produce Clifford gates, powerful but insufficient for full-fledged quantum algorithms. Previous work tried to patch the gap by introducing unreliable external operations or mixing different anion families. Those fixes often sacrifice the very topological protection that makes these systems so appealing. And this is the part most people miss. Protection against errors was traded for computational power, leaving us stuck between reliability and universality. The breakthrough comes from a group at USC, led by mathematicians Filippo Iulinelli, Sung Kim, Joshua Sussin, and Aaron D. Lauda. They propose adding a single, previously discarded anion, called alpha, into the Ising anionic mix. Surprisingly, this one extra particle transforms the whole setup into a universal quantum computer, powered solely by braiding. What's the big deal about alpha? It emerges from a non-semisimple topological quantum field theory. Essentially, the math no one bothered saving because certain representations have quantum trace zero. By avoiding semi-simplification, the team preserved these overlooked elements. Think of them as hidden building blocks that turn out to be the missing pieces in a complex puzzle. Researchers have cheekily dubbed these newfound heroes neglectons, with just one neglecton at the center. Braiding operations generate any quantum gate you can imagine. Key advances from the study. They unveiled the alpha anion that completes the universal gate set. Braiding around a stationary neglecton achieves a dense set of SU2 rotations on one qubit. They built a multi-qubit encoding scheme with minimal leakage outside the computational subspace. They extended Reichart's iterative approach to engineer two-qubit entangling gates with exponentially low error. Now, here's a question to spark debate. The proposal rests on non-semisimple TQFTs, which technically breach unitarity, a sacred law in quantum physics. The authors argue the violation hides in unused portions of the system, while the computational core remains perfectly well-behaved. Does banking on safe rooms in a mathematically unstable house feel too risky, or is it a clever loophole? Let us know. The road from theory to real devices still demands one major experimental leap: finding or engineering materials that host a stationary alpha anion. Experimentalists are already probing Ising anions in quantum Hall systems, spin chains, and more, so adding one more target might be within reach. Moreover, the theory ties into logarithmic conformal field theories, tools used to describe disordered media and boundary phenomena, hinting at unexpected bridges between disciplines. Implications stretch beyond just the new particle. By embracing what was once seen as mathematical detritus, we might unlock the full potential of topological quantum computing, robust, universal, and truly scalable. Future work will probe other choices of alpha, hunt for physical hosts, and develop algorithms suited to this unconventional framework. Is this the final piece for a fault-tolerant quantum future, or are we opening Pandora's box by relying on non-unitary trickery? Share your thoughts below. Do you see Neglectons as quantum computing saviors or its wildcard gamble? Unlocking universal quantum computing with Ising anions beyond traditional TQFT. Harnessing the power of non-semi-simple topological quantum field theories, TQFTs, is opening new doors for achieving universal quantum computation through braiding mechanisms, something that traditional, semi-simple models struggle to do. At the heart of this breakthrough lies the realization that even the well-studied Ising anions, associated with the realm of fractional quantum Hall effects, can be extended to support complete computational universality solely by braiding, diverging from their usual limitations. But here's where it gets controversial. Conventional Ising anions are known to only facilitate Clifford gates via braiding, which isn't enough for universal quantum computing. Extending this capability has called for complex supplementary protocols involving error correction or unprotected operations. What's revolutionary about the recent work is that it leverages the richer structure of non-semi-simple theories, mathematical frameworks that do not simplify representations away, that inherently possess more potent topological features. In particular, by moving beyond the classic unitary modular tensor categories to non-semi-simple categories, researchers have found new anion types, labeled by a real parameter alpha, that, when included, allow for pure braiding to generate any gate needed, including the elusive non-Clifford ones, thus achieving universality without extra tricks. This approach hinges on an essential insight. Non-semi-simple TQFTs avoid the process of semi-simplification that would otherwise discard infinite families of representations, instead embracing them via a renormalized quantum trace. These theories produce invariants that are even more powerful and can support complex anion models with fusion rules akin to, but more extensive than, the Ising model. For example, adding a single new anion type alpha, indexed by a continuous real number, permits the entire computational lie to be realized through braiding alone. However, it's not all smooth sailing. These models generally involve products that are indefinite, meaning that the underlying Hilbert spaces risk losing their positive definite status, an attribute usually fundamental to physical interpretability. Nevertheless, in specific sectors, particularly for certain ranges of alpha, the computational subspace remains positive definite, and braiding acts as a proper unitary operation. This partial positive definiteness is crucial because it suggests that, despite the theoretical complexity, we might still find physically realizable systems supporting these exotic anions. Furthermore, this framework employs sophisticated algorithms, adapted from the Fibonacci anion error correction techniques, to construct low-leakage entangling gates, methods essential for scaling up to multi-qubit systems. These techniques rely on controlled braiding operations that depend on fusion outcomes, which can entangle qubits, while minimizing unwanted interactions with non-computational states. Intriguingly, these advances could be just the tip of the iceberg. The theories connect deeply with logarithmic conformal field theories and logarithmic vertex operator algebras, all areas that have seen a renaissance in recent years, hinting at experimental pathways in condensed matter settings that might support such non-semi-simple anion systems. Systems at the fractional quantum Hall filling factor nu equals 5/2, for instance, remain promising candidates. And this is the part most people miss. Moving into non-semi-simple theories not only broadens the mathematical landscape, but might also lead to realistic, gapped physical phases that can host these complex anyons, something that the chiral theories, which are often gackless, typically cannot achieve. This suggests an exciting future where models once considered only mathematical curiosities could become the basis for practical, scalable, topological quantum computers. Are these non-semi-simple theories truly physically realizable, or are they just elegant mathematical blueprints? Could they revolutionize our approach to fault-tolerant quantum computing? Or will the challenges of indefinite unitarity prove insurmountable in real materials? The conversation is just beginning, and your perspective could be the next piece in this groundbreaking puzzle.